And before jumping into Hadoop, I would just talk about decision support systems. So decision support systems, these are the systems which should enable any organization to make a decision. And typically we are looking at a dashboard which is showing multiple charts, bar graphs, donut graph and all. So based on these graphs, you would analyze the data that is existing in your system or in your organization. So maybe these charts are coming up from data warehouses or data marts. So what decision support systems do is they compile useful information that is there existing in the organization, and then it would provide it will enable organizations to identify and solve problems and to make better decisions in promoting or improving their business. And how do they do is they typically use data warehouses or data marts, and they even do those computerized decision support systems. So this has been there for quite some time, and people are comfortable with this. But as of now, the data is being increasing. So we have the new term called big data. I'll go to the next slide. So what is big data? Big data is all about this volume, velocity, and variety. If you see, in early 1980s and 1990s, most of the data that has been generated was from ERP systems or customer CRM systems, and during that time, storage per GB was around $1,900, and by the time it came to 1990s, it was the storage cost has come down to $9,000. And typically, all those systems, they would use applications for payroll, inventory, those kind of systems. And during this time, volume was about 10 million gigabytes. And then the age of web has come, the decade from 1990 to 2000, and storage cost has come down to $15 per GB. And this is where we have mobile data coming into picture, e-commerce data coming into picture, digital marketing, weblogs and all. So that with advent of Web 2.2, again, data has increased from gigabytes to terabytes to few petabytes of data. And now, the current order of the day, we are in the Internet of Things, the age of Internet, where devices communicate with each other. They are generating a lot of data, social analysis, clickstream data, sensor data, devices talking to each other. So the data that is there has been exploded. So if you see the typical characteristics are, when you talk about volumes, there are terabytes of data, more number of records coming into picture, transactions, tables, and files. And when we see the variety earlier, the systems, ERP or CRM systems, they are typically structured systems where they were generating structured kind of data, which were typical row column data, and then later it came to semi-structured and unstructured. Semi-structured are more like XML data, which define data or like content of the data, and unstructured are the social media data, the notes or text or the tweets or chat people would do. And the last thing earlier from batch, when we saw like near time and then real time, and now we are talking about streaming data. So to handle these kinds of huge data, we need a new mechanism. Let's see how, these are some of the characteristics I just spoke about. So these are the various systems that have been generating data, and we need to provide insights on these data. And let's see why big data is really important. So earlier, when there were people flying to planes, they had this for frequent flyers. They had those reward points for the miles they were traveling. Earlier, maybe it was for some time it was a luxury. Only a few people have provided it, but later it has become obvious that all the airlines should provide, because if you are not providing, people, there are many other competitors, so people would definitely go into other airlines. So right now the organizations have a lot of data. Data is available to an organization, but they are not able to completely are 360-degree. They're not able to provide a 360-degree view of the data, so they are missing the opportunity. So as they are not, the organization is not processing the entire data they are having, there is an opportunity that is being missed. So this is the thing which we want to address, the missing out, the gap through big data. So organizations are able to process a less amount of data that is being available, and enterprises are more blind because they are losing this. Now, this is something that happens in 60 seconds. I'll skip this. I mean, these are the many ways through which a customer or a user can provide his feedback or details about a product that is being launched in the market. I'll skip this. So typical traditional server storage was they were using mainframes or analytical appliances which use a storage area network or a network area storage, which again have a RAID operating system or like RAID disk array to store data and provide data. So these topologies have data in one place and processing another. So servers were doing the processing and the data was being stored in those RAID boxes, and they're overloaded for the single points for large number of client requests. When huge number of requests comes, this would be a typical bottleneck for them. And this is completely process oriented. Now, the challenges we saw that in the first slide we saw how the prices were coming down for the storage per GB. That's what Moore's law says. Processing power doubles every 2 years, and the real bottleneck here comes getting data to the processors. So the typical data transfer rates are 75 MB per second, but if it is for 100 GB of data to be transferred to a processor, it would take approximately 22 minutes. So I mean, it may be worse than this. So we need new systems to handle this. That's where Hadoop has come into picture. Okay, we'll talk about Hadoop origination. It all started with Google. Google has published a paper in the year 2003. It is on MapReduce and Google file system. It talks about massive amounts of handling clickstream data, and based on this white paper was given by Sanjay Gimawat, and based on this white paper, duck cutting has created Hadoop in year 2006, and the primary requirements for Google file system or MR was, it has to scale to petabytes of data and to thousands of nodes, and it has to be highly fault tolerant and simple to program. Because if you see all the Google data centers, they are huge number of commodity hardware that is being used, and the hardware failures are most common. And Google search engine, they use crawlers which would crawl across multiple various websites and fetch all this data, and they have to store the data and immediately provide results for their searches. And the two primary components of Google file system were GFS and MapReduce. Google file system is for storage and MapReduce was for processing. GFS provided the distributed and fault-tolerant systems that were required for this kind of processing, and MapReduce is the programming framework which would work on this distributed programming. So in 2006, duck cutting started Hadoop, and the primary components of Hadoop are HDFS and MapReduce. HDFS are for storage and MapReduce is for process. And this little yellow elephant, this guy, he's named after his son's toy elephant Hadoop. And duck cutting was actually working on a project called Nudge, which was an open source search engine. And to to store and process, he required a better system, and that's when he started Hadoop based on Google file system and MR white paper. So what we are seeing on this screen right over here is a Hadoop cluster, which is of commodity hardware. It is not a high-end appliance which need a high-end configuration. These are the normal computers that we have at our domestic purposes. And the primary feature of Hadoop is the scalable data storage and processing framework. Hadoop, Apache Hadoop is a top-level project in Apache software foundation. It is all open source. Open source meaning the source code is free for development, and its most important feature is it is distributed and it is tolerant to the faults, because we are using commodity hardware. These hard disks and these RAMs, they tend to fail. They can fail at any point of time. So even if the hard disk fails, the data that is being running on this disk has to be replicated in another disk and then processed. So we saw that HDFS and MapReduce are the two main parts. So I'll quickly go through the ecosystem. So in Hadoop ecosystem, we have HDFS at the bottom layer, and it is a storage layer. And HBase is an NoSQL database. Again, it is for storage, and MapReduce is for programming. And Hive and Pig are applications which are used to process data on HDFS through MapReduce. And Scoop is another component which would provide data ingestion from RDBMS. So Zookeeper and Avro, these are other components. Primarily, Hadoop sits on a Java virtual machine. So underlying on every machine on a computer node, you would have a hardware, and hardware you'll have some operating system, may it be Linux, Windows, or Mac. And inside it, you'll have a Java virtual machine running. And in JVM, you'll have your actual Hadoop instance running. Excuse me. So a typical computer would have a hard disk, a RAM, and then a processor. So all the instructions are processed using RAM and stored on hard disk. And if you see, I'm talking about operating system, which is of Windows, and it has application. It is we are talking about Microsoft suite of applications, a Word application, Excel application, PowerPoint application, Access. Based on the requirement, I can use any of those applications to store and process the data. So on a hard disk, we store data in file system. So the storage medium on a computer is a hard disk, and the processing is being done by applications like these applications. They are processed in using memory, and this memory hard disk handshake is being performed by operating system, that is Windows. So what it typically does is it reads instructions that are there in the hard disk and runs an application. These applications in turn read data from the file system, and they would load them into main memory and then process them. So this is the typical processing and storage that is being run on any of those computers or a commodity hardware. So as the number of applications increase, we need more memory and more data for storage. For storing more data, we need more storage. So to scale up a system, we simply add memory and storage. So the limitation over here is for a normal computer, you have for Windows, we'll have a 8 GB or 4 GB RAM lockdown, and for hard disks, you can scale. Nowadays we can scale up to terabytes, but this data is not. This hardware is not really efficient to compute the organization or enterprise level data. That's where Hadoop would come into picture. So Hadoop has a storage layer as HDFS, and processing, it has multiple components. We will look into it in detail. So these processing and storage are being run by a framework called MapReduce. This would do it in a distributed fashion. So if you see, a node is a typical computer which has hard disk and RAM. So this is your storage area and this is a processing. So you have multiple such nodes put together form a Hadoop cluster, and then all of them together would provide a single layer for storage called HDFS, and on top of it for processing you'll have MapReduce framework. These are few ecosystem components. Like Avro, Shukwa, HBase, Hive, Mahout, Pig, and Zookeeper. HBase is a NoSQL database. Hive is for data warehousing, SQL-like. Mahout is for machine learning. Pig is for again computation, parallel computation, which is more like a C kind of function-based language. It is a high-level data flow language. I'll skip this common Hadoopable programs because I want to show Hadoop, a small demo on Hadoop. So these are the things which we can do using Hadoop. So typically I'm showing recommendation engine over here. So this is an Amazon website which would tell based on your previous buying patterns or searching patterns, it would recommend items or products or items or products which other users are related to your search. And this is all based on the data, huge amounts of data. And this is a LinkedIn recommendation. So I'm not getting deep into this. So I think I'm clear with this core Hadoop basics. So I'll jump into HDFS and MapReduce now. So we will see how HDFS is playing a really important role over here. So HDFS stands for Hadoop Distributed File System, and it is the collocation of storage and processing. It stores and processes data on the same nodes, and it brings computation to data, whereas we saw in NAS or SAN, wherein data is being brought to processing node and then processed. So we are overcoming that bottleneck. It reduces input and output I/O and boosts the performance. And as we are talking about commodity hardware, we still have hard disk latency, and disk streaks are expensive. So what we would do in Hadoop is read a lot of data at once and then process it. We already saw this, and this is HDFS is optimized for Hadoop, that is for distribution or distributed file system. Values high throughput much more than low latency. So throughput is more important than the latency over here, and we saw it is running on Java JVM, and there are many. The HDFS is similar to Unix-like file system. It is hierarchical and Unix style paths and permissions, ownerships. So HDFS is the bottommost layer where you store data, and on top of it you would perform processing using MapReduce framework. So HDFS primary goal is to scale data and assumes both hardware and software failure, and it is targeted for a small number of very large files. We are talking about huge files and less number of files. That's because we write once and read multiple times. We look into this in detail. And same, we have files and directory structure, traditional hierarchy, and it's highly portable. You can use any of those operating systems. It follows typical master-slave architecture, where we have in Hadoop we call the slave as a data node and master as a name node. So we have a data node daemon running to track the slave operations and name node daemon for master. So a large file is being split into multiple small files, into blocks, each of this is 64 MB. This can be changed, and these blocks are being replicated into multiple nodes because we assume that hardware or software has faults and they can fail at any point. And if you see typical appliances, all those rack servers, they cannot scale up beyond a point, whereas here we can scale across. So the replication factor in Hadoop is by default is 3. Each block is being placed in multiple nodes. If I think, like, if you can visualize this node 1 and node 2 are in the same rack, and if node 1 as in a different rack, so Hadoop would place blocks, the first block in one node and the second block in another node, and the third replica in a different rack, because there is a chance that there will be a failure at a rack level. Similarly, it would place all the other copies. So we have a write affinity. First block, once copied, it would copy into the second block, and this second block would in turn replicate into the third block. So the second copy is written into a data node in the same node, same rack, but which is very close to it, so that it can reduce the cross-rack network traffic and within-rack network traffic. And the third copy is sent into a different rack just to tolerate the switch failures. The entire objective of this block level replication is for load balancing, faster access, and fault tolerance. So a name node will have a secondary name node as a backup node, which would do checkpoints, and data nodes are the slave nodes which are responsible for storage of the block level. So name node will give the address of each of those data nodes and where exactly to store, and a client would be there. A client would talk to name node, and name node would give the data node directory locations. So a client would directly copy into data nodes. You will see in the coming slides. So in HDFS, this is how it follows. So name node talks to all the data nodes that are available in the cluster through Heartbeat. It would check whether the data node is up and running, and name node would provide balancing and replication. And these data nodes, they would store the data and write them into the local hard disk of those nodes. And typically the large file that we were talking about is split into multiple files, and it has to be stored in all those data nodes. So the file is copied initially into HDFS client, and HDFS client would talk to name node and get the data node locations, and then this file would be split into smaller blocks and stored in those data nodes. This is how it is being done. You see there are multiple splits, and these splits, it has been copied, replicated 1, 2, and 3. Similarly, all the blocks are replicated. I'm just going fast, I want to quickly cover this topic. And then getting files is also similar. First, HDFS client talks to name node. Name node looks at all the blocks of a particular file that are being stored in different nodes and gives all their locations, and they are again client directly reads from the data node and forms the file back. And as we said, we are using commodity hardware, and his software can also have faults. So it can be a disk failure, or an entire rack failure, or a switch failure, or a name node itself. If there is a name node failure, we have a secondary name node, and in the latest version, we are talking about HDFS high availability and YARN. So we have even more flexible options for handling those kind of failures. We'll see how typically it does. Say for example, if this entire data node, say 1, 2, 3, 4, data node 5 has entirely failed, and on data node I have blocks black, gray, and green. So I have to replicate them, or like do load balancing. So by the heartbeat, name node does a heartbeat, and data node sends. If a data node is not sending heartbeat back to the name node, it assumes that the data node has failed, and name node has already stored all the metadata about the data node and the blocks that are being stored in the data node in its memory. So it will immediately replicate those blocks into another data node like this. auto-replicated and remaining nodes satisfy the replication factor. So still at any point of time, we have a replication factor as 3. And once the data node is back, again, okay, what if the name node itself is failed, we still have a backup node. We can do an image and we can get back those details. And once we scale up using another node, the node rebalancing is done automatically. So the name node does it again. So detects the new data node that is being added to the cluster and copies the blocks so that the existing nodes are no longer overloaded. So this is how node rebalancing happens. To summarize, HDFS is for high scalability. It can be scaled to thousands of nodes with massive amounts of data, hundreds of petabytes of data, and typically we use large block size to maximize I/O performance. We no longer require high-end appliances like RAID and all. Simple mechanism of block replication still suffices the RAID functionality. Block locations and record placement is invisible to the end users. That is about HDFS. I'll quickly go to MapReduce. So MapReduce is a programming framework which would work on HDFS. So it removes the burden of distributed computing from the developers. Earlier, when it was distributed computing, developers were supposed to, write how the tasks have to be split and then move to different systems. But with the advent of MapReduce will take care of this. So it has two primary functions: map and reduce. Map does a splitting. It does a divide and conquer. So and reduce, it combines and reduces the function, the data. So all we have to do is write the map and reduce functions. We need not worry about the underlying distribution, fault tolerance, rebalancing, and all that stuff. For which it takes MapReduce take care of all fault tolerant and scalability. And so what it typically does is a map function would split a large file into multiple subtasks and perform a function, and a reduce function would combine all the output from those map tasks and perform an output. So as you see in the picture, this is the map and this is the reduce. This example, okay, I'll go through this example. So this guy, our Sam over here, he wants apple juice. So he uses a knife to slice the apple and make a juice. And this a big apple is being sliced into multiple small slices and reduced into juice. And later, if he wants to do this to an entire basket of fruits, so a map function would be used to slice the fruits, and each fruit-related slices are put together and then given to a reducer, which would give output as a juice. So this is how a map reduce would work. A list of values are mapped into another list of intermediate list of values, which will be reduced into a single value. I'll just skip this. So typically how a map reduce works is like this. So on each data node, a large file is already being split on each of those data nodes, and based on the key value pairs, a mapper would create intermediate keys and values, and a shuffle and sort will happen, and this data would be distributed to reducers. And then output will be coming. So I'll talk about a word count example. The primary components, before I go to the word count example, the primary components of MapReduce are a job tracker and task tracker. A job tracker is like a master and task tracker are like slaves. This is similar to HDFS, where in HDFS you have data name node and data node. So job tracker keeps track of task tracks, and these task trackers are responsible for running the tasks on the local file system on the data. Okay, so this is how it looks on HDFS layer and MapReduce layer. HDFS is like storage and MapReduce is for processing. So for HDFS, you have.
Hi Prashant.
Yes.
Sorry to interrupt.
Yes.
Davi here. Prashant, I feel if somebody doesn't know about this Hadoop framework, it will be very difficult for him to understand this at this space. So I understand these things because I already know these things. I'm currently going through some courses. That is my personal opinion. So
yes, Sharat, correct. Oh, Sharat, like this is generally for training I used to take, but I have only 1 hour, so I was rushing.